Good evening, guys. I have just gotten back in not very long ago from a Scholars Bowl tournament, so I've been all across the county. So, as you can probably guess, I'm pretty tired. But I did not want to not forget and not post a video just kind of recapping some of the complex number stuff that we discussed in class past a day or two. So, I'm going to flip my screen around here and we're going to take a look at a few little thingies about the complex numbers. So give me a second here. All right. So one thing we discussed in class was the cyclical pattern that that exists. Give me just a second. Let me. I'm just gonna go through the first five here. So we know anything raised to the zero power is one. So out of the zero is just get a little better light here. Is just one. I to the first is simply I. I squared, as we know from our definitions, is negative 1. Now, let's think about I to the third power. If I remember my laws of exponents, I can rewrite this as saying the product of I squared times I to the first, because 2 plus 1 is 3. So I know I squared is negative 1, and then I to the first is just I, right? So I have a negative I. Right. So for I to the third, I to the second, I to the first, and I to the zero. And likewise, I can show I to the fourth to be, I can show it to be I to the third times I to the first. So now I know I to the third was my negative I times my I to the first, which is just I. So I'm going to come over here because I'm running out of room. So what that's saying is negative 1 times I squared. Well, I squared is negative 1 itself, right? So really I'm saying negative 1 times negative 1, which is 1. If we go further, let's take I to the fifth. I can rewrite that as saying I to the fourth times I to the first. 4 plus 1 is 5, right? Well, we know I to the fourth is 1. I to the first is I. So there's I. So at this point now, you should be able to start seeing some sort of a pattern unfolding in your numbers. I'm noticing 1, I, negative 1, negative I. And then look here again, 1, I. I'll bet, let's do another one. Oh, heck, let's just do two of them, why not? I'll bet anything, I'll put money that I to the sixth is going to be a negative 1. Let's see. So if I say I to the fifth times I to the first, that will be I times I, which is I squared, which is negative 1. Lo and behold, it does seem to be unraveling like that, doesn't it? All right, so I to the seventh, that'd be I to the sixth times I to the first. So I to the sixth is negative 1 times I, which is negative I. So what we're starting to see unfold here is 1, 2, 3, 4, 1, 2, 3, 4. We're seeing that cyclical pattern. In other words, here's what's going on. If I call this I to the 0, which is 1, I to the first, which is I to the second, which is negative 1, I to the third, which is negative I. I'm seeing a pattern unfold, a cyclical pattern unfolding every time I make a revolution. So, those were some of the things that I brought to light in class. I also discussed how, and I actually misspoke when I said this in class earlier. I called it a modulus. I was actually thinking of another thing, so I want to correct that real quick. But let's take I to the 255th power. Okay, I showed how, like, since I know there's a pattern of 4 every time, I can take this exponent power of 255 and I can divide it by 4. Now, I'm not necessarily worried about the quotient. What I care about is the remainder. That's what I was calling the modulus, and I misspoke there. So let's see, that's going to be 25, that's going to be 6, that's going to be 24, that's going to be 1, 15. That's going to make that a little bit darker there. Oh my gosh, that's horrible, ain't it? Okay, that's 6. Say 4 going to 15, 3 times, that's going to be 12. Okay, so I got a remainder of 3. And what I showed in class is that the remainder of 3 correlates to the exponent value. So I to the third is negative I. So in other words, I to the 255th power is equal to negative I. That's your answer. Okay, so that was one of the things that I discussed in class today. And then once we understood, once we understood how these right here worked, we came over to a problem like this. Now, I've got a lot going on here, so let's. But one thing I do know is that it's all multiplying, so that's good. I can kind of do this how I want to. So since I'm the one doing it, I'm going to FOIL these first, and then I'm going to multiply by 6. So if you remember FOIL first, which is 28, your outers, which is negative 14i, your inners, so that is minus 24i, and a positive 12i squared. So that's inner and last. So we go through here now. Remember, all this is got to be multiplied by that 6 at the very end. So the overview of this, one thing you need to really take away from this is that you are doing the same algebra that you did in your 9th grade or 8th grade year, as far as how you handle this. Now, the only new thing is the fact that you have i's and I squareds and all that in there. But structurally, it's the same. So you got 28. Okay, that's going to be a minus 38i plus 12. All right, now, here's the kicker. I squared is really negative 1. So that's going to be a negative 12. Okay, so 28 minus 12, so that's going to be a different 8, so that's going to be 6. 16 minus 38i. Then I'm going to distribute that 6. So, brain shutting down tonight. 16 times 6 is, okay, it's going to be 96. 38 times 6 is a negative 228i. So there is my complex number. And just for the sake of simplicity here, now I also later on showed, well, actually, I was going to use that, but I'm going to do a different problem for that. I also went through and showed how the complex number field, actually, I call it the Argand plane, which is actually the name of it. It was real and imaginary axis. So if I had the point, the number negative 2 plus 3i. This being the real part, this being the imaginary part, I discussed how you can actually treat that as like it were a ordered pair. So the real part, go back negative 2, the imaginary to 3i. I'm just gonna write it like this right here. It should be a negative 2 plus 3i. So that's how you plot a complex number on the Argand plane. Then I went on to discuss how if I want to know the distance here, and one thing I guess it just kind of hit me. Um, I feel like I failed to make this connection, and I think it's a pretty dang good one. Um, we discussed this, so it was discussed in class. How about the absolute value of a complex number? Think about it. We know absolute value is the distance from zero on a number line, right? Well, think about this. This really um, is I say this very loosely. It's the number line, but it's not really line. It's a plane. Now it's a complex number plane. This right here is I'm finding the distance from the origin to that point. I'm finding the absolute value. Kind of like you remember back when we'd find when we had absolute value of x is 3. We knew that it was like here's 0, here's 3, here's -3. 3 units either way, right? Well, think about it. Remember, real number axis, that's all we're dealing with. Now we've expanded our understanding of numbers. So essentially, we're talking about the same thing. It's just now we're looking at complex numbers. So to find the distance, here's what I'm doing. I'm taking the square root, because the reason I'm using the whole square root thing is I'm working off the distance formula, because I am talking about 2 dimensions here. So the distance formula is how you handle this on a plane. So I'm taking -2 and I'm squaring it. Then I'm adding the 3 and I'm also squaring that. So you've got 4 plus 9, 13, square root of 13. So your distance from the origin to here is the square root of 13. Or if you were to approximate that, 3.61 units. So think about that. If each one of these tick marks were inches, from here to here, that'd be 3.61 inches. Yeah, if you want to look at it in that kind of context. Sometimes it's weird looking at a square root going, okay, how's that a measurement of distance? What does square root of 13 even look like? If you approximate it, you kind of get the idea what they're talking about. But yeah, so I didn't even actually think about explaining that this morning. I guess my brain was in a fog. Is it a huge deal? Like, oh crap, I don't know that on the test. I'm gonna fail. No, not that. If you know how to do this, you're fine. But I did want to make that connection there for you. I thought that was kind of interesting. So we also talked briefly about the complex conjugate and all that. So I don't want to. Well, I'm going to spend a little bit of time explaining that. It's not on the test tomorrow, but hey, why not talk about it? So I'm going to say 3 plus 2i, 5 minus 7i. So was doing a problem like this, and remember the complex conjugate is this right here. So if I have a complex number, its complex conjugate is going to be that. Basically, the sign changes. So I'm looking at this. Now, the reason that I'm even going through all this is for this reason. We don't like, in mathematics, we really don't like i's or radicals in the denominator. It's just kind of like a burr in our butt. So if you think about it, I'm kind of saying the same thing. We know I is understood to be the square root of -1. So really, that's kind of a radical there if you just think about it. So the whole idea of rationalizing the denominator is I'm changing what this looks like and I'm simplifying it, but I'm not actually changing its value. What I mean is this right here. I'll give you just a very elementary arithmetic example. I know that 1/2 and 2/4, I know they're the same thing, right? They look different, but they mean the same thing. That's what I'm talking about when I say I'm changing what it looks like, but it still means the same thing. Man, I'm on fire tonight. Man, that's a good connection right there. Man, I should remember this stuff when I was in class. All right. So here's what I'm doing. I'm going to multiply this by the product of one really. To kind of set the stage, think about this. If I took 1/2 and if I multiplied it by 2 over 2, 2 over 2 is really just 1, right? So watch this. 2 times 1 is 2. 4 times, I'm sorry, 2 times 2 is 4. You see how I multiplied this fraction by a, um, a fraction that was actually a product of 1, and I got this? Same thing, right? Just looks different. I've not changed the value of these of the fraction. I've just changed its look, kind of like Clark Kent, Superman, right? So that's what I'm doing here. It just looks a heck of a lot cooler. So here's how I'm going to go about this. I'm going to multiply both top and bottom, by the complex conjugate, which is this. Now here's where the whole foiling and all that on the problem we did earlier is really, really flipping handy, because this makes it a lot easier. So we got 15 plus 21i plus 10i plus 14i squared. So that's 15 plus 31i plus 14 times -1. You should know that by now, that that's really a -1 there. So we got -14, that's 15, that's 31. So that's going to be a difference of 1, 31i. Okay, so that takes care of the top part. Whew. All right, so 1 plus 31i over. All right, now let's do that bottom one there. Let's 5 minus 7i. Oh my gosh, guys, y'all just have to bear with me. It is right now as I'm working this. It's 6:44, and Mr. Bess is a little bit tired. So here we go. So that's 25 plus 35i minus 35i minus 49i squared. Ah, looky at what's happening here. So those are going to cancel. So I have 25 minus 49i squared, which is -1. So really I got 25 plus 49. 9, 10, 14, 6, 7, that's 74. So let's see, 1 over 74 is not going to reduce. 31, 74 is not going to reduce. All right, so there's nothing that can be reduced there. So here's the end game. Here's what I've done. I started out with this, had that I on the bottom. Ugh. I multiplied by the complex conjugate, and you're always looking at the denominator there, because that's what you're trying to clean up. And I went through this long process to find to multiply that full amount. And so this right here, so to go back to that arithmetic example I gave, 1/2, 2/4, same thing, right? Multiplied by 2. So if I want to draw some arrows here, that was this, this, this. Like I said, and I'm sure I'll get some hate mail over this, but mathematically it's sound. It's pretty sound. Now, granted, is 2 the conjugate of 2? No, but the idea that I'm trying to get across to you structurally, it's the same. So that is what we have been discussing. Tomorrow, on tomorrow's test and all that, you want to make sure that you still remember how to, graph parabolas. Hey, if I gave you, hey, this is a little sneak peek for y'all. Those of y'all who watch my videos, hey, tomorrow I might ask you, hey, what's the range of this like a function like this? You know, the range is the lowest to the highest, so that would be a range of 3 to infinity, you know, something like that. So, you know, make sure you remember that. Make sure you remember how to find the vertex. I'm sorry, the axis symmetry. Find the vertex. Um, how to use the quadratic formula to find roots. Hey, here's a sneak peek. Always remember, if you had something like this, and I'm asking you to find the roots, remember, it has to be set equal to 0. I hope I don't have to say why I'm setting it equal to 0. Huh. Sorry. Well, it's silent there for me. I was just listening. I think it is raining. So, yeah, so some of those things, let me turn my phone back around. So, some of those things are what I advise looking over. Again, always, kudasoftware.com. Go to the Algebra 2 tab, and you'll scroll down, and you'll find like where it says complex numbers and all that stuff. Matter of fact, I'm looking at it right now. I want to show you. So I'm go. So you look here on the left side and you find Algebra 2, and right there it is. That's a good place to find some study materials. So I'm going to leave this with you. Good Lord, 22 minutes. Dang. All right, so y'all have a great evening and happy studying, and I'll see y'all tomorrow.